Good morning. I welcome you all to this session of fluid mechanics. In the last class, we discussed about the forces that is being exerted by a fluid jet impinging on a flat and curved surfaces. Now, today we will again see that the application of momentum theorem to a control volume, by the application of the momentum theorem to a control volume, we can solve many other practical problems of interest. Today, first we will be discussing the principles of jet propulsion. What is principle of jet propulsion? This is a principle based on which the aircraft moves, the movement of aircraft in air and sometimes the movement of ship in water are based on this principle of jet propulsion. What is this principle? If you know, probably you know from your popular knowledge. For example, an aircraft, when it moves, it takes air from the ambient. So atmospheric air comes into the aircraft, and where this air is used to burn a fuel which is being injected into the aircraft, and these burning products, the products of combustion at high temperature and pressure. First of all, air is compressed obviously by a compressor, so that a high pressure air is delivered before it burns with the, before it is mixed with the fuel to be burned, and then combustion products is being expanded through a nozzle at very high velocity, and these products of combustion or burned gases at high velocity is ejected from the nozzle at the rear part of the aircraft, and this gives the propulsive force or the force for the aircraft to move. That means if the aircraft had to move with a constant velocity, this force should balance the air drag at that velocity. Otherwise, the air will accelerate or decelerate. So this is precisely the principle of propulsion. In case of ship also, moving ship takes water from the sea, then it is being ultimately pumped to a high pressure, and then it is being expanded through a nozzle at the rear end of the ship at high velocity, and due to the ejection of high velocity fluid, the ship experiences a propulsive force in the direction of its motion. So this is the precise jet propulsion theorem, and as you just can understand from this is purely based on the Newton's second law of motion, second law and the third law. What is that? Because some fluid element which comes into the system, for example aircraft or ship, gets its momentum change, that is the momentum is increased, because it is coming with a low velocity and getting discharged with a high velocity. So this due to this change in momentum, the system experiences a force exerted by the system. Well, so simply the second law of motion by Newton, and then by the third law, the same magnitude force but in opposite direction is being given by the fluid element to the system, that is a ship or an aircraft, which is precisely the propulsive force which allows the vehicle, aircraft or ship, to move. So now if we, based on this principle, if we see, now let us see this principles of jet propulsion. Principle of jet propulsion. What is this? Principle of jet propulsion. Well, now let us see that this is like this. If we have a jet, it is, first there is a compressor. Let me draw the layout or block diagram of the component like that for a just better understanding. So this is the compressor C, compressor COM. This is the combustion chamber CC. So this is the turbine, one turbine is there, and this is the nozzle. This compressor and turbine is actually attached to a same shaft, but I am doing like this. Now basically from fluid mechanical point of view, what happens if we consider this aircraft is moving with a velocity v in this direction, okay, for which the air comes in to the aircraft. That means relative to the aircraft, the air comes in with the same velocity, that I will write afterward. So because of its motion, let the aircraft is moving with uniform velocity v. Air comes into the aircraft. So first it comes to a compressor. The first component of the aircraft engine is the compressor. You will learn this thing afterwards in your applied thermodynamics class, that air comes to the compressor which compresses the air at high pressure. So we are not much interested about the mechanism and processes of each and every equipment, but you should know that in general After compression, the compressed air is being allowed to flow through a combustion chamber where fuel is injected, fuel is injected, fuel is injected, and the air reacts with the fuel is burned, and a high pressure and temperature combustion product gas is being discharged from the combustion chamber. Then it comes to a turbine. As you know, it will be also taught the next year in the fluid machines class. The turbine is a machine which develops work while the fluid flows through it and the pressure of the fluid is decreased. That means we can tell that it is an expansion process. The fuel from high pressure expands to a low pressure, high pressure and temperature expands to a low pressure and temperature, and some amount of work is being developed, and this work is utilized to drive the compressor, because compressor requires work to compress a fluid from a low pressure to a high pressure. After that, the fluid comes out of the turbine, still it has got a high pressure and high temperature. So this energy of the fluid. Now what are the forms of the energy of the fluid? So as you know, we have recognized the mechanical energies are pressure energy, kinetic energy and potential energy. But here kinetic energy is very small, the velocity is very small at this plane, that is after the discharge to the turbine, that is there is a nozzle at the end, so at the inlet to the nozzle. So only energy is the pressure energy, and another energy is the intermolecular energy because of the high temperature. And the sum of this U plus P by rho, you will know afterwards in your thermodynamics class, is known as enthalpy. So therefore these two terms of energy comprises, this two term of energy constitutes the total energy of the fluid, which is being utilized in terms of the kinetic energy. That means an expansion through a nozzle takes place where the pressure and temperature are decreased to a low value, and the ultimately fluid comes out to a very high velocity. Let this is the velocity of ejection of the fluid, VE. This is the principle of jet propulsion. Okay, this is coming out with a velocity VE. Now you see that what happens is a high velocity jet is being ejected. Now again we should know that under certain circumstances the pressure at the exit plane may not be equal to the atmospheric pressure. If this be atmospheric pressure and the pressure at the exit plane, let is P2, sometimes P2 may be greater than the P atmospheric. It may be equal to P atmospheric and greater than. I am not going into detail, but I just tell you that if it depends, now question comes that whether the velocity is above the sonic speed or not, that is supersonic or subsonic or sonic. The answer to this is, this depends upon the relative magnitude of the pressure at the inlet to the nozzle and of the atmosphere. That means if for a corresponding ambient pressure the inlet pressure above a certain critical value, then the expansion is possible up to supersonic level, otherwise not. So if the inlet pressure corresponding to a given ambient pressure is below a certain value, certain maximum value, so supersonic speed is not possible. Supersonic velocity is not possible by the expansion of this fluid to the ambient pressure. In that case, only a converging nozzle will serve the purpose. But while this pressure is higher than a maximum value corresponding to a atmospheric pressure, then the expansion of the fluid up to a supersonic level is possible, and in that case only a converging duct will not be sufficient. Then a converging and diverging duct is used as a nozzle if we want the expansion up to supersonic level. But in that case, if we restrict the expansion only to a convergent nozzle, then it will give expansion to a sonic level. So sonic to supersonic expansion is possible through a diverging duct. It is just the reverse in case of subsonic flow. When the area decreases, the velocity increases, but in supersonic flow, when the area increases, velocity increases. So there, if we do not provide the divergent duct, say expansion will be stopped up to the sonic level, and in that case it will not be expanded up to the atmospheric pressure. In that case the pressure at the exit plane will be higher than the atmospheric pressure. This as information you know. Sometimes what we do, that even if the atmospheric pressure and this inlet pressure is such that supersonic expansion of the gases up to supersonic velocity is possible, even if it is so, sometimes it is not allowed like that. It is allowed to expand only up to sonic velocity through a convergent nozzle, so that P2 becomes greater than P atmospheric. And in some cases it is not so, a convergent duct is also used, so that the expansion up to atmospheric pressure is allowed, where the discharge plane pressure becomes equal to atmospheric pressure and the velocity of discharge is supersonic. This is just because your information, otherwise you will not be able to understand when you will be analyzing the control volume and control volume theorem, momentum theorem for the control volume, that why P2 is greater than P atmospheric. So certain cases P2 may be greater than the P atmospheric, this is the P atmospheric. Now here the problem, this is with this information for this jet propulsion or jet engine performance. Now we can think this problem from the basic fluid mechanics point of view, that fluid element comes with some momentum and is going with a different momentum which is more than this, so that a fluid element suffers a change in momentum in this direction, for which the fluid element experiences a force exerted by the system, that is the entire aircraft engine, in this direction. And as a Newton's second law, according to Newton's second law, reaction force opposite in direction but equal in magnitude is exerted by the fluid to this nozzle, propelling nozzle, or the entire system. This nozzle is known as propelling nozzle, and that is the propulsive force which is being experienced by the aircraft and which is responsible for its movement in the forward direction. So therefore, what we do now, our next part, simply from the fluid mechanical point of view, we recognize then what we recognize? We recognize a control volume of fluid, just we do inside the aircraft like this. Let us draw this control volume. Okay. Here let us draw where, let me draw here the control volume. Let is the control volume. Okay. So this is the control volume. So this is the control volume. So this is the control volume, CV. So now here also again you can recognize, since the aircraft is moving with a velocity v in this direction, so control volume is also moving, and we will have to analyze with respect to this moving control volume. So therefore, the analysis will be made with respect to moving control volume. Only with respect to moving control volume the flow appears to be steady, because here at fixed point the flow velocity is 0. But for example here at fixed point the flow velocity is v, but when this going out the flow velocity becomes 0 at a long distance. That means we have to move with the aircraft to see always a flow velocity v here and always a flow velocity v here in this direction. That means a person sitting on the aircraft will always see at the inlet air is coming with a velocity v. If it moves with uniform velocity, he will always see a liquid fluid going out with a velocity not v, v minus v, that is the relative velocity, this is fixed. Okay. So therefore, to make the problem steady, we have to analyze with respect to the control volume. Again and again I am telling, that is the reason for which the analysis is made with respect to the moving control volume. Let us consider these as the axis, x and y. Let two axes attached to the control volume. This is the control volume. So similar analysis. So now with respect to the control volume, that means if we make the control volume fixed, that means the aircraft fixed. That means in other words we give a velocity v in the opposite direction. So that means with respect to the control volume, the air is coming with a velocity v and it is going out with a velocity v minus v, which we call as u, that is the relative velocity of the jet, exit jet, fluid jet with respect to the aircraft. Now the pressure here is Pa, at this plane pressure is P2. Now it is very simple. What is that? Let if I consider Fx is the force acting in this direction. Fy we are not very much interested, because this will be balanced by the weight, because the aircraft is moving in this direction. So we are interested in the force exerted or force exerted between the control volume and the aircraft, mutually between control volume and the aircraft only in this x direction. So therefore write the equation. What is this? That net efflux of the momentum in the x direction if m dot is the mass flow rate of air. Now here one thing, if I neglect the fuel mass flow rate, usually fuel air ratio is very high. Sometimes we can take or sometimes we can neglect. Okay, let us consider mf dot. mf dot is the rate of burning of fuel, rate of fuel burn we can consider. So, therefore, this is usually very small. This is the total mass flow rate at the discharge times the velocity u minus m dot a u, that is the m dot a v, that is the momentum influx. Efflux positive direction u, influx positive direction v with the minus sign is equal to Fx. Now, we know that we have to add the pressure forces with their gauge values if we finally want to arrive at the net force acting on the aircraft, taking care of the atmospheric pressure forces exerted on it. We have seen that earlier, that if we do not take the gauge pressure, absolute pressure, find out the pressure exerted on the control volume of fluid, then minus of it is the pressure exerted on the system, that is here aircraft for example. Then if we add on it the effect of atmospheric pressure on its side, then we see it is same as if we find out the pressure force exerted on the control volume with the pressure as the gauge pressure at these two sections where the fluid coming in and going out. This already we have established earlier. So, therefore, we take it with the gauge pressure. So, this is 0. So, only pressure is this P2 minus P atmospheric, that is the gauge pressure. P2 is the absolute pressure if we consider P2 minus P atmosphere into, let A2 be the area of the propelling nozzle at its discharge plane. So, simply this is the equation. All right. So, we can write Fx is equal to m dot A plus m dot F into u minus m dot A v plus P2 minus P atmosphere into A2. Usually this is very small. In usual aircraft engine, the air fuel ratio is even sometimes 120, 60 to 120 in this ratio. So, sometimes we can neglect this, and if we neglect this, then we can write a simple expression like this. So, this is simply the P atmosphere. When in case of a subsonic expansion, that means when the fluid is coming out with a subsonic velocity less than the acoustic speed, when Mach number m less than 1, then the expansion takes place up to completely the discharge atmospheric pressure, because when it is discharge to atmospheric pressure, we consider the pressure at the discharge plane is always atmospheric pressure. So, within the scope of our syllabus for this fluid mechanics class, we are considering only the subsonic flow. So, always whenever there is a flow situation which is coming out or discharging at the atmospheric pressure, so discharge plane pressure is always atmospheric. So, this part will be 0. But there is a phenomena which you will learn afterwards, when the fluid flows with both in subsonic and supersonic regime. That means, in that case what happens, if the outlet pressure corresponding to an inlet pressure is such that the fluid may be expanded up to a supersonic velocity, then if it is to be done, we have to add a convergent part and then a divergent part, and a typical design length is there, up to which it will be convergent, then it will be divergent. So, if you do not do, if you only provide a convergent duct, then what will happen, the fluid will be expanded only up to sonic velocity. It will not be expanded up to supersonic velocity, and in that case it will be unable to utilize the entire drop in pressure. That means the pressure will not be decreased up to the ambient pressure, and this will be coming to a pressure at the discharge plane which is higher than the ambient pressure, and immediately there will be a pressure drop after the fluid is being discharged into atmospheric pressure. So, only under those situations, so P2 is more than P atmospheric. Otherwise, you may feel difficulty that why at the discharge plane, when it is discharged to atmospheric, pressure is taken more than atmospheric. This is precisely the information. This condition is known as choked flow condition. Choked flow condition. This will be told afterwards in the class of compressible flow, choked flow condition, when this choked flow condition. So, P2 will be greater than P atmospheric. So, in that case only we will get this. So, this is known as, now before that I tell that what is then Fp, that is the propulsive force on the aircraft. Now, you see the Fx is positive. U is greater than V, P2 is greater than P atmosphere. That means the force on the control volume is acting along the positive direction of the x axis as I have taken. So therefore, the force acting on this aircraft will be in this direction, that is minus Fx. That means this is the direction of the its motion. So the propulsive power P can be written as Fp into the velocity, the uniform velocity. So this analysis is valid for this aircraft moving with an uniform velocity, because the control volume is an inertial control volume moving with uniform velocity. So this is the propulsive power expression. So this part of this thrust, propulsive thrust or propulsive force, is known as momentum thrust. This is known as momentum thrust, momentum thrust. And this part of the thrust is known as pressure thrust, which is generated due to the pressure thrust. Now you see that this is the expression for the propulsive power. Now consider a situation, what happens in rocket. In rocket, the difference between a jet and a rocket, in a jet engine, probably you know from your popular knowledge, what is the difference between a jet engine and a rocket engine? Can you tell what is the difference between the operation of a jet engine and a rocket engine?
Rocket engine maintains its own fuel, sir.
Rocket engine takes
Its own fuel and oxidizer.
fuel is also there, oxidizer, very good. That means fuel is also there within the fuel tank in the aircraft, but oxidizer, that is the oxygen required for burning of the fuel, is taken from the atmosphere. Yeah. For a rocket, both oxidizer and fuel is contained within the rocket. That means for a rocket, from fluid mechanical point of view, it does not take ambient air. So in that respect, that means generate propulsive power, its performance is independent of the atmosphere, atmospheric condition. That means there is no influx, that means this is zero. That means though rocket is moving with a velocity v, but this influx momentum is zero, because no air is coming. There is no provision made where the air will be sucked in or air will be taken into the vehicle. So therefore, which part will be zero? This part will be zero. So for rocket engine, so the analysis is that this is the rate of the burnt gases coming out of the propelling nozzle of the rocket, plus if there is a pressure thrust, is equal to the force exerted on the control volume, or opposite of that is the propulsive force. That is the only difference for the operation of the rocket engine. Okay, clear? Now I will tell you what happens in case of accelerating non-inertial control volumes. Now I will come to the application of non-inertial control volume. Non-inertial control volumes. Propulsion of ships with uniform velocity in sea water is also based on the same principle, so that you can see in the book. So I am not discussing that. Now I come to the non-inertial control volume. What is non-inertial control volume? The control volume which is accelerating. Now consider the situation that jet engine is accelerating, not moving with uniform velocity. That means propulsive force is always more than the drag resistance of the air at that particular speed. So the speed is going to increase. Similarly, rocket engine is also accelerating. It is not only fixed for jet engine, but rocket engine also. So in that case, we will have to analyze the situation by a momentum theorem applied to a accelerating control volume. But usually, the momentum theorem is very difficult to applied in a accelerating control volume, because the usual transport theorem which we write, that for principle of momentum, that is the net momentum a flux plus the rate of change of momentum within the control volume, that is valid for a control volume which is either fixed or moving with uniform velocity. So this has to be modified by taking into consideration the inertia force of the control volume. But usually when the accelerating system are analyzed, then it is analyzed on the basis of system approach. That means your usual approach, conventional approach, the rate of change of a particle or rate of change of a system, rate of change of momentum of a particular system is equal to the force acting on this system in that particular direction. Now before that, after that I like to tell that why we are not doing, this is valid now what I will be doing for any accelerating system, but usually jet engines moves with uniform velocity. So therefore uniform velocity analysis, that analysis for with inertial control volumes are all right, but accelerating systems are only the rocket. Why? because rocket at its initial during its initial flight, it is accelerated to a very high velocity. The reason is that rocket contains its own propellant. What is propellant? Propellant is the fuel and the oxidant. And if rocket has to travel a long distance, so it has to carry a very huge propellant for its travel. So therefore, at the initial part of the rocket flight, the extra work that is being done to raise this huge amount of propellant is usually wasted. So therefore, what is done to have the effective use of the material, as much as propellant has to be burned to attain a very high velocity during a small interval of time. That means during the initial flight of the rocket, for any rocket flight, the rocket is accelerated very high. So this high acceleration of the rocket at the initial part of the flight is very important and has to be analyzed to find out the acceleration which is required, what will be the amount of fuel to be burned, all these things which we will not go into detail at this present moment. But you must know, so during this initial part of the rocket flight, rocket is being accelerated. So therefore, any analysis during this part cannot be done with respect to an inertial control volume. So therefore, what usually is done, this type of system is being analyzed with respect to a system approach, and this is not only for a rocket. So in books you will see always they describe the non-inertial control volume analysis for a rocket engine. That does not mean it is only for rocket engine, for any accelerating system. So how it is done for a rocket engine, let us see. Now let us consider a rocket like this. Let us consider the propelling nozzle, and it is moving vertically up, and usually does so. Let us just symbolize the rocket like that, which is moving at any instant. Its velocity is v. At any instant t, let its velocity is v. Now gas is ejected. Gas is ejected at a velocity let v. It carries its fuel plus oxidant. There is no doubt in it. So that means fuel plus oxidant, which is known as propellant. This is the terminology, probably you know, propellant. Okay. Now how it is analyzed, because if you make a control volume, it is accelerating, that means the velocity is changing. This is the instantaneous velocity v at any time t. So it is analyzed with respect to system approach. What is the system approach? It is very simple. It's a school level thing. System approach. Let at this instant t, m is the mass of the rocket along with its propellant, because the total mass of the rocket is mass of the rocket plus its propellant. So m is that mass. And let us consider after a time delta t. Let at the time delta t, the burning rate of the fuel is constant. Let that is m dot f. That is the burning rate of the fuel, or rather I will tell that burning rate of the propellant, m dot, not fuel, burning rate of the propellant. Okay. So this is the burning rate of the propellant. That means this is the rate at which the spent gases, burning rate of the fuel and the combinedly with air, that means the burning, this is the rate of reactants participating in the reaction, or you can tell this is the rate at which the burned gas is being ejected. All right. So now after a time delta t, we consider that velocity v is changed to v plus delta v. That means the velocity is increased to delta v. Well, now then we can write the system approach equation of motion, that is the rate of change of momentum, rate of change of momentum, rate of change of momentum of the system. Now you ask me that, sir, what is the system? Now I take this system, that is the system approach. You must understand at t, the rocket and its propellant at time t comprises the system. So therefore, at time t plus delta t, this system comprises a mass within the rocket which is m minus m dot delta t plus a mass m dot delta t which is coming having a velocity v. Okay, that is the exit velocity. All right. So therefore, the momentum of this system at time t plus delta t minus momentum of the system at t divided by delta t will be the rate of change of momentum of the system of the system of the system. So, rate of change of momentum of the system is equal to the momentum of the system at time t plus delta t minus the momentum of the system at time t divided by delta t. Now, what is the system? Let us recognize at time t plus delta t system approach. If you recall, it contains the same amount of mass with same identity. That means identity has to be traced out. So, what was our system? Our system was the rocket and the fuel and oxidant whose mass was m at t. But now the system after t plus delta t will be this mass. Now, after time delta t, the mass of the rocket and the fuel is m minus m dot delta t. So, this m dot delta t amount of mass which was originally there within m is now appearing, if we trace its identity, in the exhaust gas, this m dot delta t with a velocity v. So, therefore, the momentum of the system at time t plus delta t is m minus m dot delta t, okay, into v minus m dot v plus, sorry, I am sorry, v plus dv, I am sorry, m minus, I have not talked about this mass, and this is having now a velocity v plus delta v, I am sorry, v plus delta v, then plus m dot delta t, this is with velocity v e. So, this is the momentum v, why v minus v? No, not relative to the system approach I am doing. Why you are doing relative to the rocket? You do not get confused. This is m dot v, so v in this direction, so you are correct. So, if you write the momentum here velocity is in this direction, so because of that you can make a minus sign. So, this is the momentum of the system at time. You must follow, this is a system approach. We are finding out the momentum, net absolute momentum of the system. Why you are making a relative velocity? Earlier we used the relative velocity because we analyzed with respect to a control volume which is moving to make the system steady in a control volume analysis, but here we are making a system approach for an accelerating system. So, it is simply the rate of change of momentum of the system, absolute momentum. Now, what is the initial momentum? Minus m v. It is clear? There is no doubt in it. This is the change of momentum. Okay, this is the change of momentum. Is there any doubt regarding this change of momentum? Please tell me. There is no question of relative velocity. It is only the change of momentum of the system which is accelerating. That is why I have taken for a time delta t the change in velocity. This is precisely the momentum of the system. It is a typical system approach. So, system which was, what is the system? That is the m mass of fuel and oxidant plus the rocket at time t. So, this system comprises this mass with v plus. Initially the system was m mass, again I am telling, of the rocket plus fuel and oxidant moving with velocity v in this direction. This direction I take as the positive direction. So, after a time t plus delta t, what is this system and what is the associated velocity? System comprises m minus m dot delta t mass with v plus del v velocity and m dot delta t mass with v velocity. Its form and thermodynamic states are not important, its mass and the associated velocity. Why minus? Because v is in the opposite direction. We consider this v is the exit velocity in this direction. So, minus the initial momentum mv. So, therefore, rate of change of momentum will be limit of this value, limit of m minus m dot delta t into v plus del v minus m dot delta t v e minus m v, all right, divided by delta t tends to 0. So, is there any difficulty in this? So, I can write this as the rate of change of momentum. So, rate of change of momentum of this system is this minus this divided by delta t. For a delta t time, delta t tends to 0. Now, if we make this, you will get mv and mv cancels. So, you get m into delta v by delta t. So, therefore, we can write this expression simple mathematics, limit m into delta v by delta t and minus m dot into what we can write delta v, m dot into v plus delta v plus v e times delta t divided by delta t. Delta t tends to 0. So this delta t cancels. So only trick is that when delta t tends to 0, this also tends to 0. V is constant, so this is all right. So the limiting value will be v plus v, where delta v also tends to 0 when delta t tends to 0. So delta t cancels. But here delta v by delta t, so this tends to 0, this tends to 0. So according to our calculus, so this represents the rate of change of velocity with respect to minus m dot v plus v. So this is the rate of change of momentum. Okay? So this is the rate of change of momentum. Now what is v plus v? Just I see. In physical system I described v is the velocity in that direction and v is the velocity of the ejected gas. These are all absolute velocity, system approach. So therefore v plus v is the relative velocity of the jet with respect to the aircraft, with respect to the rocket. So therefore this is usually written in the terms of this is equal to m dv dt minus m dot u, where u you can write the relative velocity of jet with respect to the rocket, relative velocity of jet or exhaust gas, whatever you call exhaust gas with respect to rocket, So this is the rate of change of momentum. So this rate of change of momentum now will be equal to m dv dt according to system approach. It will equate with what? It will equate with the net external force acting in the same direction. So momentum is accorded into the vertically upward direction. So momentum is accounted for in the vertical. So what is the net upward force acting in the vertical? So what are the forces? That is the weight at any instant, weight of the rocket at any instant, that is m. So that may be minus mg plus the pressure forces. That means if the pressure here is P2, which is higher than the atmospheric pressure, if the atmospheric pressure is P atmosphere, so P2 minus P atmosphere into the area of the propelling nozzle plus P2 minus P atmosphere into area of the propelling nozzle. Now, if the gravity effect is negligible, so it is only the pressure difference which gives the net force to account for this change in momentum. Okay. So this is precisely the net force acting on the rocket which is causing its change in momentum. So this is done with the help of system approach. Of course there is a resistance force. You can write, sir, why not? Air resistance. If there is any resistance force, air resistance is there. So it is the difference in pressure. So if the rocket goes to space where there is gravitational effect is negligible, so there is no resistance, so it is only the pressure difference times the propelling nozzle area which gives the external force to the rocket and responsible for its acceleration. So there will be plus Fr. Fr is usually in the opposite direction to its motion. That means Fr will be there with a negative sign. So there will be the minus Fr. That is the air drag resistance. That means when rocket is moving in the ambient, so this is the atmospheric drag, so resistance force. That means in general, this part we will have to recognize from the physical system that what are the different forces acting on the rocket. That is equal to the rate of change of momentum of the rocket at that instant. So this is the system approach. Now after that, I will come to a most important section of this chapter, is that motion with uniform acceleration. Of course, time is limited for today's class, which is most important topic that I will be describing in the next class. That just I tell you brief that now we will discuss certain flow situations where fluid is accelerated or moved with uniform acceleration or velocity. If fluid is in motion, it is with uniform motion. That means all the fluid particles will be moving with the same velocity. As I told earlier, this is the case of pure translation. Or if the fluid is accelerated, it will be accelerated with uniform acceleration. For example, a tank containing fluid is accelerated horizontally or vertically or in any arbitrary direction. Then what happens? We can consider the fluid within the tank is accelerating uniformly. That means each and every particle on the fluid is accelerating with the same value, same acceleration. Another case is the pure rotation or solid body rotation. That means if a fluid body is rotating about a axis in such a way that all fluid particles are moving with uniform angular velocities. Uniform angular velocity, that means a solid, the way the solid body rotates. This happens in practice if we take a fluid into a cylinder, and if cylinder is giving a spin, is rotated about its axis, then the fluid within the cylinder will be churned, will be rotated in a way that it will give a solid body rotation. That means the fluid will be rotating, each and every particle of the fluid at different radius will be rotating with the constant angular velocity. So that the tangential velocity at any point will be defined as the angular velocity times the radius, that it will bear a linear relationship with the radius. That is the basic equation of the tangential velocity for a solid body rotation. You understand? So these situations we will be analyzing in the next class, how the pressure varies in these cases of fluid flow. That if fluid is uniformly accelerated or uniformly moved, or a fluid is given a uniform rotation, that means a solid body rotation or a rigid body rotation, what is the pressure field within the fluid. Okay, this will be our discussion in the next class, because time is up. I cannot start this because I cannot finish it. Okay, thank you.